Good morning. Hopefully, you guys have had a great first unit back from this semester. You guys should have by now completed those passion projects, and pretty much all of them are uploaded, I think, to the main slide. So if you want to check that out, everybody came up with some really awesome ideas. So that would be kind of a cool thing. That's the whole idea is I wanted you guys to go ahead and look at those, kind of see what other people's interests are, and maybe you'll see something that you weren't aware of before now. So we're going to go ahead and get into this is unit 6, not unit 5, vibrations and waves, and a little bit with sound. So today we're going to be talking mostly about simple harmonic motion, which this is kind of a throwback to earlier in the year. We did use this relationship, this formula already. So force is equal to the spring constant times the displacement. So the only difference now is that we're applying this relationship to a different like a different set of values. So instead of talking about just like forces necessarily, like something being stretched down, we're going to be applying that to the motion of waves. So we're going to start out talking about springs, obviously, because that's the easiest way to visualize this, but we're also going to apply this to sound waves, like simple pendulums and things like that. So again, this was Robert Hooke. He was the one that came up with Hooke's law. He also is widely known in biology. That might be where you recognize his name from. He was the first person to ever come up with the word cell to describe the cells in living organisms. So he was the first guy that took like a slice of cork and looked at it under a microscope and called that a cell. So anyway, he was kind of widely known in many different areas, but he came up with Hooke's law also, which describes the relationship between a spring constant and the displacement that gives you the force of that object or that spring. So you can see that here in this little GIF or GIF, however you say these, right? You do have your displacement, obviously. And so as this object is displaced, the spring has some displacement. Okay, so we are stretching the spring out, and then it always comes back, it always restores back to its original position. So you can see how the displacement changes, the velocity and the acceleration can change as well. And then you guys can also think about the potential and kinetic energy changes there, right? So when it is pulled all the way down, we have a large amount of potential energy and low kinetic energy because it pauses briefly. Then as it starts to come back up, you lose some of that potential energy, but you gain that in kinetic energy. So your simple harmonic motion, by definition, is going to look at any periodic motion that's the result of a restoring force. So what that means is it's a motion that happens over and over that can be timed. Okay, a period is like a time frame. And then that's going to be the result of a force that's acting on it that is within the system. Okay, so the restoring force has to be provided by the spring or by the string, like this pendulum system that's happening. So that's kind of important because you can have periodic motion caused by other forces, right? So if you pick up your pencil right now and you move it back and forth in front of you, technically you're moving it in a periodic motion, but there's no restoring force there. Your hand is moving the pencil, right? So specifically talking about a restoring force that exists within the system already present, that is causing your motion. So we know that because every harmonic motion involves a restoring force, which would be given to you here by the spring in this example, every harmonic motion is going to be a back and forth motion over the exact same path. So you can kind of judge this by the amount of displacement given in the beginning. So we know that we have this x here is going to be our displacement. So however much we displace this spring will determine the amount of force that the restoring force is going to have, right? So if we increase x and we're multiplying that with the spring constant, if we increase x, which is our distance, that's obviously going to increase the restoring force of the spring. So these are a lot of terms we've used already, right? So we have the force coming back is dependent upon the restoring force, which is your your spring constant times your displacement. We have the mass of whatever object is here. We also know that this relationship exists, and then our displacement. So we've talked about all of these things before. So just keep in mind that your simple harmonic motion means that it's going to be repeating over and over and over along the same pathway until it runs out of energy. Okay, so here is an example. So if a mass of 2.1 kilograms attached to a vertical spring stretches the spring 6.2 centimeters from its original equilibrium position, what is the spring constant? So we have the mass is 2.1 kilograms. We're going to need to convert this into grams, right? We want everything to be in grams. The distance, we've converted the 6.2 centimeters into meters. We know that gravity is 9.81. We don't know what the spring constant is, and that's what it's asking for here. So here we have these two relationships, and we're able to derive our own formula from that. Okay, so we know that if force is equal to the spring constant times the displacement, and then we know that force is equal to mass times gravity, we can derive our own relationship. So we're going to substitute these in. We have K times the displacement in meters set equal to the mass in grams times, we've got this in kilograms. I probably need to look at that. All right, so here is one example. So if a mass of 2.1 kilograms attached to a vertical spring stretches the spring 6.2 centimeters from its original equilibrium position, what's the spring constant? Okay, so we know what we're given. We know that the mass is 2.1 kilograms. The displacement needs to be in meters, okay? So we converted the 6.2 centimeters into meters, and gravity is 9.8. We're trying to find the spring constant. So we have these two relationships. We know that force is equal to the spring constant times the displacement, and then force in another sense is also the mass times gravity. So because of that, we can derive our own relationship here, our own formula, and then substitute in our values to solve for K. So we know that K is the spring constant. We're going to have K times the displacement set equal to the mass times the gravity. And this is going to tell us that our spring constant for this specific spring is going to be 332 Newton meters. Okay, so this will always be dependent on the type of material and the shape of the spring, like if it's tightly coiled or loosely coiled. K can change depending on the situation, but you can use K over and over again within that same system if you're trying to solve for something different. So we saw some examples of that last semester when we were looking at, and I know we had a couple questions about like a bungee jumper, right? So if a man jumps and you figure out the spring constant for that person and their weight, and then you have a different man with a different weight, you can calculate then like how far he's going to stretch the bungee or whatever other information you could figure out his mass or vice versa. Okay, so with simple harmonic motion, you're going to stretch or compress the spring, and that's going to store elastic potential energy, which is the restorative force, okay? So mechanical energy is conserved in springs. So here's an example of this here. If anybody's familiar with cars, you do have like your shocks, right? So they're absorbing some of that force, but they have a spring constant, and it's probably a very high spring constant, but it's not so stiff that you still feel every single bump. So there's kind of a fine line there. Another example here would be a bow, like a compound bow. So, if you draw back the bow, it's going to store potential energy in this string, right? So if you think about it as a whole system, you've got the bow, the arrow, the string, all of the other pieces involved there. So when it's at rest, when you've pulled it back and you're waiting, the kinetic energy of the system is zero, but you have a high amount of potential energy because you've pulled this back, and the draw is going to be however many pounds, like 60 pounds or 75 pounds or whatever, and you have an immense amount of potential energy waiting. Then when you release the string, that potential energy is then converted into kinetic energy. And the moment the arrow leaves the string is going to gain most of the potential energy stored in the bow. So that's going to return the system to its original amount of potential energy. So if you want to think about this in terms of that spring constant or Hooke's law, We know that if you increase the distance would be one thing. So the longer your draw length is, and also the amount of force that's being applied, can your spring constant can change. So if you have like a higher spring constant within like your setup, your string here, and you have a longer draw length, that can increase the force being applied. Simple pendulums are also examples of simple harmonic motion. So we know that a pendulum is going to have a mass and a string. So the mass is usually called a bob. It's referred to as a bob in physics. And you know that your simple harmonic motion is always proportional to the restoring force. So it's the same thing with a pendulum. Your motion can never be greater than what it starts at, because if you're just having this as a pendulum system, you're not adding any additional forces after it starts, then the energy, eventually you're going to lose a little bit of energy with each swing back and forth, right? You're losing a little bit of that motion. So eventually it would come down to zero, and it would fall back into its place and sit still again. But with this, you can always have a restoring force that's proportional to its displacement. So if you if you swing a kid on a swing and you pull them back really far, they're going to swing a little bit further than if you just push them just a little bit. Okay, so here's a couple videos I wanted to show you. This one, this is a demo that physics teachers do sometimes. I have yet to try to attach this to the ceiling in this classroom because I'm a little bit afraid of what could happen. And I'll show you what could happen on the next clip. But this does a really great job of explaining the physics behind this.
I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at zero speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it zero speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
Okay, so that's an example of when it worked well.
I am such a strong believer.
Get this into the next slide here. So this is an example of a fail. So like he said, you have to add zero force whenever you're dropping this pendulum. So in this case, I'm not sure if they added a tiny bit of force or if this girl moved, but it did not work out so well for her. Okay, so that's terrible. Obviously, the sound just gets me every time. Looks like she moved forward a little bit on that, but if she would have stood completely still, it would not have hit her, because you cannot, as long as you drop it with no additional force, there will not be enough energy for it to come back to its original restorative position. She moves because she's back here. And she moved about 4 inches forward. Oh, just enough to get her. Okay. All right, so let's go ahead and watch the next one.
Count.
This one I'm just throwing it in there because it showed up with the recommended videos. This is another physics teacher demo that is just another one of the things that people don't do very much anymore because of things like this. So this is supposed to show how forces are evenly distributed. This is a piece of wood with some nails sticking out under it, and he has a cinder block and a student with a it's supposed to be a sledgehammer, but it looks like it's an axe. And the student has the ability to hit this cinder block and break it, and it's supposed to, evenly distribute the force. It's not going to hurt the teacher because he has all those nails down here. But this one, there's a little bit of a mishap.
1, 2, 3. You didn't hit it. Okay. Right here, ready? All right, take that off. Okay. Well, the first swing took a piece down south. Sorry. That second one hit pretty good, though. So.
I'm not even going to watch that again. So anyway, that's why some of these risks I just am not willing to take. Obviously, that could have gone wrong in many ways. It could have hit him anywhere. Poor guy just got hit right in the worst place. So anyway, your simple spring systems, these are going to be the ones that we've been looking at this year already. So you have a mass affixed to one end of your spring, and it's more controlled, right? So if you had down here, like you have a spring scale, right? We're measuring the amount of newtons of force being applied. So the magnitude of that restoring force is obviously, again, it's going to be proportional to the distance that you're displacing the spring. So that's here like a scale. That's how scales work. So you are getting on these scales and you're compressing these little spring sensors that they have inside. And the more you compress them, they know that there's a set spring constant of those springs. So that is used in the calculation. So if you apply a certain amount of force and they use the spring constant, they can figure out how much you weigh in pounds or kilograms or whatever it's measured. Another good example is like a pinball machine. Hopefully, I would assume most of you have played with these at one point in your life. And that's it, okay? So if you so feel inclined, you can go back and watch some of these fail videos again. These are in the slides. But as of today, we're just going to be working on some more practice questions using this relationship with simple harmonic motion and Hooke's law. In the next couple of classes, we'll do a lab using Hooke's law that specifically looks at different spring constant and kind of a little different viewpoint on it than what we looked at it from last semester.